going to tell us about his hack.
Yeah, it's a nasty hack too. All right, so about 7 years ago, we had a client come up to us and he asked us, or they asked us, to debug some memory leak that they had, which we do regularly. I didn't think much of it, which turned out to be the start of a very long and arduous journey figuring out what was going on, which eventually led to a blog post called Sharing Space Leaks, Conduits and Friends, which I wrote 7 years ago, which I can only describe as utterly depressing. This made me kind of lose faith in Haskell in a while. Which is why I've titled this talk a workaround for one of the most important problems in Haskell today. Now, of course, I might be a bit biased, haven't thought so much about this problem. My colleagues might call me obsessed with it, but let's see. I do think it's an important problem. I have no solutions. I have a workaround, which is a hack. So this is as much a call to action as anything else. So what is the problem? We have a lot of data in our programs that are not really data per such, but more things that drive computation, right? They're not storing user information or things like this. They're telling our code what to do. And so a typical example is like a conduit, right? Or a pipe or things like this, which is a data structure. You can think of it as a domain-specific language, which is describing incremental computation, right? For example, we might want to stream stuff from a database into a WebSocket, and we don't want to do this by first reading everything into memory and then streaming everything to the client. We want to do this row by row, right? And typically, one way to do this is to have an abstraction like this, which is a DSL. You describe your computation in this DSL, and then you have an interpreter of this DSL, which executes it hopefully in constant memory, right, without growing everything in memory at once. So this is control data, right? This tells our code what to do, with the express goal of making sure that we can have streaming computations in constant memory, which is why it's all the more ironic that this client came to us and said, actually, we have a memory leak, and the very thing that we're leaking is this very abstraction intended for incremental computation, and a memory leak of type pipe in this case. Now, this is, you never want to see this, right? Pipes should never be built up in memory, right? If you see a memory leak where you have a bunch of pipe in memory, then you already have a problem. So how might this arise? And I want to simplify hugely here, because the problem is quite subtle. So I'm going to consider sources. Like a source is like a conduit which only yields values, right? So this is almost like a list. Right, we have a const constructor, which in this case is called yield, and then the nil constructor is done, and in this case, done also carries a result. And so, for example, yield from here is a conduit or a source that yields all the values from n down to 0. And then we have a very custom interpreter for this thing, which just runs the conduit, and what does it do? Every time it yields a number, it adds it to some accumulator, and then when it reaches yield, it just returns the accumulator. Right, simple enough. Then I might have a simple test case, which constructs a conduit, which yields the values from 250,000 down to 0, executes it, right? Adds up all the numbers and prints it, or in fact, ignores it. This program runs in constant space, right? As expected. No problem so far. Now I'm going to have a minor variation on this program. I'm going to run an exception handler around this. What is the exception handler doing? It runs the computation. If it returns a result, it just returns it. If an exception is thrown, it will just rerun it again. It's a bit contrived, but just to show the principle here. In this example, just to point out, the exception handler is never run. No exceptions are thrown, right? So that is not the problem. However, it doesn't know that in advance, right? So in order to be able to run the computation again, it needs to hold on a reference to this computation. So as the computation runs, retry holds on to this action. In this case, what is that action? Well, it's run source C. Therefore, by holding on to it, it's holding on to the conduit. Therefore, as we are running this conduit, GC can't collect the conduit as we're unfolding it, and therefore we're building it up into memory. Right, so this thing has a memory leak. And then you might say, okay, well, maybe let's just try to make sure that this conduit is allocated every single time that we run this action, right? Rather than allocating it up front. So you might try to move this in, right? Having the let binding inside this retry thing here. And you will try it again, and you will find it makes no difference whatsoever. And okay, what can I do now? Okay, maybe let's turn it into a function, right? Maybe retry doesn't take an action, it takes a function that returns an action, maybe a function from unit, just to try and encourage this program to not allocate this thing up front, and you will find it makes no difference whatsoever, right? When you go down this path, you will lose your sanity very quick, right? Forget it. It's not going to happen, right? GHC does not give you tools to determine when something is allocated. There's passes in GHC for laziness that move stuff out of lambdas. There's passes like the state hack that moves things into lambdas. You have no control over this. Maybe we can come up with a language in which we do have control over that, but I think that's, as far as I'm concerned, not something I want to think about, because I think this is an assumption that's deeply ingrained in GHC that is quite difficult to change. And remember, even if you manage to do it in your library by very careful code, all of your upstream code that uses your library will also need to do it, right? This is not a solution. What you can do instead is before you pattern match on a conduit, you first duplicate the thunk. Now, dup.io is a primitive from a new package that we released last week. It's a fork from a very old package called ghc-dup, which is long since defunct. And what it does is it duplicates a thunk, right? So it just makes a copy of it. Why does that help? Well, when you think about it, if we start evaluating this conduit, we reduce that thunk, right? It starts out as a thunk, right? We reduce it to weaker normal form. We then update the thing in memory, and we move to the next one, right? Then we reduce that to a weaker normal form, and so forth. So we're building up this chain of pointers from the head to the next one, to the next one, to the next one, right? That is the thing that we're building up as we're executing it. By pattern matching on it, by copying it first, the original thunk is left as a thunk in memory. It doesn't point to anything, right? Then we pattern match on the copied thunk. We reduce that to weaker normal form. But since this is a local copy, nothing else is retaining it, so it can be GC'd straight after, right? So by copying it before we pattern matching on it, we avoid constructing it in memory, right? In a way, and this is foreshadowing a little bit, we don't want this thunk to be updatable, right? This should be a non-updatable thunk, ideally. And by duplicating it, we can sort of do that in our code. Now, that's unpleasant to have to think about this sort of thing, and it gets worse. To show why, here's a minor variation on this, which is called a bidirectional source. And the point here is that we yield a value, and then to continue, we don't have the next source. We just have a function that takes some value from downstream and then gives you the next bidirectional source. And again, we might have the same yield from constructor. In this case, we don't need anything from downstream, so that new b prime parameter is unit. Okay, fine. Nothing changed. And then we might try to write our interpreter in the same way that we did before. Right? So in our go function, we first duplicate the thunk, and then in go prime, we pattern match on the duplicated thunk. Right? We just did the exact same thing that we did above. However, this code does not work. Why not? Well, if you think about it, when we are calling go again here, the thunk that we're duplicating is the application of the function to the unit argument. That is the thing that we're duplicating, which is not the thing that we should be duplicating, because that's not the thing that we were retaining in the first place. What we would like to do is evaluate that application, apply our function to unit, just enough that we get access to the underlying bidirectional source, and no further, then duplicate that, and then pattern match on it, right? We can do that by adding an additional indirection, right? We define some sort of box. Then our function is going to return a boxed bidirectional source, and then when we pattern match on it, we call our function apply unit, get the box out of it, get the underlying bidirectional source, duplicate that, and move on. Now, if you're thinking to yourself, this is awful, I completely agree with you, right? This is not nice. And it's very difficult to get right, because if there's some other thunk in the middle, we might be duplicating the wrong thing again, right? I told you I have no answers. I only have hacks. If I had answers, I would probably be, I think there's at least a PhD or two in here to properly solve this. Now, just in case you're thinking, well, maybe this is easier for conduits if we have conduits that, like functions that really depend on their input. right? Intuitively, that should be the case, because then GHG can't pre-allocate the next thing, right? So maybe we have an example here where we have a pipe, that's a more general thing, and what does it do? It waits for a character from upstream. If upstream tells it there's no more characters, then we're done. If upstream gives us a character, then we just count it and we move on. But GHG looks at this and says, well, actually, this expression here doesn't depend on anything. Let's move it up. Right? So it moves it, it pre-allocates it before the await constructor. And so now what we have in memory, if we have this counter here that starts out as a thunk, we start executing it, right? We pattern match on it. We find out it's this await constructor, which points to a function, right? Which then in its closure points to a thunk, which is the next await constructor. Then we pattern match on this. So that also becomes an await constructor, which points to a function, which points to the next one, right? And so we get the same sort of chain of constructors. Before we had a yield pointing to a yield pointing to a yield. Now we have a yield pointing to a function, which in its closure points to a yield, right? But it's the same thing. And then, I mean, you might think, well, maybe if a character makes a difference, maybe if we do different things for different characters, then surely it can't do that anymore. So maybe we're only counting spaces, right? So if it's left, we're done. If it's a space, we count it. If it's not a space, then we don't count it. But GHG says, well, actually, no, this doesn't change anything at all. Both of these expressions can be pre-allocated. It moves both of them up, right? And now things get much, much worse. So for example, if I run this counter and I first feed it 1,000,000 spaces, then I do that again a second time and then a third time, and then I feed it 1,000,000 A's, and then I do that again and a second time, a third time, then the profile looks something like this. When we start feeding it the first 1,000,000 spaces, we're unfolding that part of the conduit, that path through the conduit. Then we count it again. Now the memory stays flat right here, right? Because this part of the conduit is already in memory. Then we start feeding it A's, so we get more memory allocated, a different path through this conduit. Then when we do that again, it stays flat, and then finally the whole program terminates, right? So we have 1.6 gigabytes of pipe in memory for this simple application. And it gets much worse, because every different permutation of spaces and non-spaces will explore a different path through this conduit. Right, so this thing has absolutely terrifying memory usage. Now we can fix it in the same way by having this box thing and duplicating before we pattern match, right? So the same solution works. Side note, you might try to write a smart constructor that every time that you construct a yield constructor, you insert a call to dup. So dup is the unsafe perform IO version of dup.io, right? Just a pure function of it. That doesn't work. Because when we're constructing this thing, we're now inserting a call to dup. Okay, so now if you interpret this thing, we would interpret that particular thunk, which is a call to dup, to we get normal form. Okay, you get the copy, but now the original thing is in memory, is now updated. Right, so if you were to interpret that same conduit a second time, the very same constructor would now no longer have a call to dup around it. And so then the first time you're fine, but the next time you're not fine anymore. You could try to have the call to dup in the destructor, right, which is a bit better. That might work, but it's very dangerous, right? Because GHG will unpack this and inline things and move things around, and dup of something just looks like a pure expression to it. Maybe it gets shared by something, right? Not advisable. So it's much better to use dup.io or dup.st where you are explicit about when and where you want to duplicate. Okay. I want to show you a different application of the same idea, which is a bit more subtle, perhaps. Here's an example of a program which processes lists, right? It processes a list of integers. What does it do? If the list is empty, it finishes. Otherwise, it drops 5 elements from this list. And you should think of this as modeling, we're processing some part of the list, right? So this is a thunk, we pull 5 elements from this list, we do something with it, and then we're done, right? So then we call perform minor GC. The idea is that this is all short-lived data, right? We literally just allocated them because we just processed them. So we call perform minor GC to make sure that all that stuff is deallocated again, and we go and we move on to the rest of the list. Okay? Then we have a small demo, which has 2 lists in it, left and right. Both have 5 elements in there. We process the left, and we process the right. Okay, let's look at what the heap does with this program. We start processing the left list. We have 5 elements, right? As we pull from this list one by one, our heap grows, the next element gets allocated, the next element gets allocated, and so forth. Then we call perform minor GC. All this stuff we literally just allocated, so it's short-lived. We deallocate everything, the heap goes down back to 0. Okay, looks good, as expected so far. Then we do the same thing for the right list, and we see the same pattern. Okay. Now I make one tiny change to this program. Instead of having 5 elements in these 2 lists, we have 20 elements in these 2 lists. Should be the same thing, right? So let's look. We run the program. We start processing the left list. 5 elements get allocated, deallocated, we're good. The next 5 allocated, deallocated. Next 5 allocated, deallocated. Next 5 allocated, deallocated. No surprises. Then we start processing the right list. We see 5 elements allocated, but no deallocation. Then the next 5, and the next 5, and the next 5, and no deallocation is happening at all. What is going on here? Why would this happen? Right? The only thing that I changed is how many elements are in these lists. It's crazy. Well, I said we expect this to be short-lived data, right? GHG uses a general generational garbage collector. We have multiple generations. And so all this stuff from these lists, we expect to be in the young generation. Right, we just allocate it, perform an GC, deallocates it again. But this left and this right thunks are both allocated before we start processing. So when we start processing the left list, we have many calls to perform minor GC. At some point, GHG says, well, actually, this right list you had is not short-lived anymore. I consider it long-lived. I'm going to promote it to the old generation. Once that has happened, from now this point forward, every moment, there's a link from the old generation to this new allocation, right, to this newly allocated chunks. And so minor GC cannot clean this up anymore. From this point forward, only major GC can clean up anything of these lists. It's awful. Now, this is, of course, a contrived example, but this is a distilled version of a real application. We have a big server for a client, which has a ton of live heap data. Occasionally, the server writes some stuff to disk, right? It does that by writing CBOR. How does the CBOR library work? It takes your data, it constructs an intermediate representation, which is basically controlled data, right? It's not data that we're interested in for the sake of the data, it's interested for the sake of driving our computation. It then writes the CBOR, and then this intermediate representation gets written to a binary representation to disk. Right? What is the CBOR intermediate representation for a pair? Well, it's the CBOR representation of the left part and the CBOR representation of the right part, just like here. Right? So then we start writing. These things may be big, and so at some point, that right part gets promoted to the old generation, and at this point, minor GC cannot clean up after us anymore, and so every single time that we need to do these GC, only major GC can clean up. But that's very expensive because this server has a ton of live data, none of which is changing. So, what's the solution? Well, we can do the same thing. In a way, it's another instance of the same thing, right? We have control data that we don't want to be in memory, that we don't want to be retained. So, same idea, same solution. What we can do is we duplicate the thunks before we process them. Right? Now we still have this right thunk in the old generation, but we don't care because it's not pointing to anything. It can live there like it's one closure. Okay, nobody cares about that. We're then working with the duplicated thing. It lives in the young generation, and so everything is fine again. So one way that you might see, this is just by the by, but one way that you might see that this is happening is that your live data is staying the same even though your heap is growing. Right? So you can see that GC is not being able to clean up. So this is based on a new package called dub.io, which is forked from the old package GHG dub. We made a ton of fixes, and I say we, this is a lot of people in well-typed have helped with this. We've been thinking about this on and off for the last, 7 years. So there's been some GC issues fixed, CAF issues fixed. It now has a very extensive test suite, tested from 8.6 all the way out to 9.6. So I'm pretty sure that this is relatively stable. There's a focus on dup.io, not dup, although dup is available, but I don't recommend it. Unlike the old package, it only supports shallow copying, right? So the old package also supported deep copying of graphs of objects. We don't support that at all. It's awful, right? I don't want to be writing code like this. This is not how I want to write Haskell, but it's better than nothing, right? I have no other solution for this kind of thing, right? Having a thing like a conduit in such a way that this sharing problem does not arise is very, very difficult. And it only happens in very small circumstances, right? And then finding out why it suddenly started happening is you can lose your sanity, right? So it's necessary, but it's not great. There is someone working on a better solution. Javier, he's a master's student. I'm supervising him. Unfortunately, he had made great progress in the beginning, and since then his employer made him far too busy, so he hasn't done much work on it since. But the idea is that you might mark some types as being non-updatable. Right, so something like a pipe or a seed or intermediate representation, you know that you don't ever want a conduit in memory or the intermediate representation in memory. This is control data, it's not data. Right, so you could mark it as non-updatable. And then the idea would be that you change code generation so that you don't update those thunks. Now that's easy enough to do if it's monomorphic because we know what the type is and so we can generate different code. It gets hard for polymorphic functions, right? If I have some let binding, let x equals blah, 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 and that blah, 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 blah is of type A, now I don't know what kind of code I need to generate. And so there's some possibilities that you might do. You might at runtime check to see what the type is, but you can only do that after evaluation, at which point it has already been black holed, so you don't have the original thunk anymore. So one naive solution, sort of a proof of concept, might be duplicate, evaluate, look at what the type is, and then replace it back, paste the original thunk back if you can. Just as a proof of concept that might actually work. But yeah, this is just research. There's no good solution here yet. Okay, that's all I have for you. If there's any questions, I'd be more than happy to answer.
Yeah, this is great. I wrote the original GHG library. It was 10 years ago. I just looked up. It was a first idea of me as a young PhD student. I had no idea what I was doing. The paper was horrible. It got rejected. I was devastated. It made it barely into a lightning talk at HIW. I just deprecated the library in favor of yours. So
thank you. By the way, your name is still as an author on the new package too. So.
Oh, cool.
Yeah.
That's very generous. Thanks. In terms of possible better solutions, GHG has the lifted kind for things that are called by name, and the unlifted kind for that are called by value.
Yeah.
So could we just have a new kind for things that are called by name, and put it in the kind level, and the polymorphic problem disappear?
Yeah.
And you wouldn't even generate the thunk allocation for things of that kind. Did somebody think about it?
Yeah, absolutely. We've been talking about this. Ben and I have been talking about it. We've been talking about it within Welltide. It would make a lot of sense to have a kind for this. You say the polymorphic problem disappears kind of by not allowing polymorphism.
Right, yeah, right? That's usually how you make problems with polymorphism disappear. But it's the same with the unlifted call by value kinds.
Yeah, but some people, in my daily work as a Haskell programmer, I never use unlifted types, and you need to have such a strong reason to use it precisely because you don't have the polymorphism, right? A ton of your abstractions no longer apply. So, yeah, it's a very sensible idea. I just don't know whether it's practical enough, but maybe, yeah. I mean, it's possible, for example, lists, right? Many lists are driving computation, right? So maybe you can have a separate type of lists that do that, right? It's certainly something that's worth exploring, I agree.
It could be one tool in the toolbox.
Yes, for sure, yeah.
Any other questions?
Hello, thank you for the talk. This looks very similar to something we're running to in the JS backend, and we're kind of sweating back here. But this isn't really a question. As far as I understand it, this is some problem that has existed since I guess for 10 years. I think we should name it. So what's a good name? Yeah, for the problem. And then the solution, whenever Javier comes up with it, is name of the problem, a solution, or something like that. So, or maybe ask Connell or ask Connor McBride, because he has punny names.
So I think there is a name for the major minor GC problem. I think it's called floating garbage.
Oh, really?
Floating garbage.
Okay, so I will just repeat the first part. Simon said that there's a name for the major minor GC problem, and it's apparently floating garbage. I was
believe
not aware of
so,
this.
from what
So,
I remember. Yeah.
all right, okay, it's good to know. Thank you. As for the name, I've been calling it the conduit problem for the last 7 years, which is probably not the best name, but that's where it started for me. So, but yeah, it would be good to have a way to refer to it.
I believe the systems term for something roughly equivalent is buffer bloat. I don't know why, it strongly reminds me of it.
Yeah.
Okay, one last question.
Would linear types help?
No. I mean, my PhD thesis is on uniqueness typing, so I'm not opposed to substructural types at all. I don't think it's a solution here. You would have to write your code in. If it's a solution in the sense that you avoid the problem, right? If you write your code in such a way that you consume everything linearly, then maybe you could set up something. But you want to write the code in the way that you want to write it, in a natural way, without having to worry about that, and it still work. So yeah, I think that's the short answer.
Okay, let's thank the speaker one more time and set up for the next talk.